Okay, in the last class, we covered IIR filter design, low pass IR filter design by impulse invariants. We discussed that in detail. Now, we will consider some other approaches also, which is this, that we will have some function HAS. Suppose an analog filter has been designed, HAS could be Butterworth, could be anything, but it is in general a rational form. In rational form, B0 plus B1s plus B2s square dot BQ s to the power q divided by A0 plus A1s plus dot say AP s to the power p. Suppose an analog filter has been designed, HAS, which is stable, causal, rational. Okay, all this has been, its frequency response will be what? HA j omega, that is, instead of s, you replace s by just by j omega. So, in the s plane, we are on the j omega axis. Suppose this is given. Then, what we do? We do a mapping. Whenever there is a s, you design a function of z. Okay, that is your design. That is where the entire intelligence lies. You design a function f z, so that wherever there is s, you replace that by f z. So, you will get a function h z now of this form B0 plus B1 f z plus B2 f square z plus dot plus BQ f to the power q z divided by A0 plus A1 f z plus AP f to the power p z. This is what you get. So, you get one form. Now, so basically you get a function of z. I want this also to be a rational function in z. This h z should be a rational function, okay, in terms of z inverse in fact, okay, rational function. It should be stable and causal firstly, and when it comes to frequency response, some more property. But before that, let us see one thing, that suppose f z itself is rational in z inverse, like f z could be just z inverse. Z inverse means z inverse by 1. So, numerator polynomial z inverse, denominator 1. It could be 1 by z inverse, it could be z. Okay, z means inverse of z inverse. It could be 1 minus z inverse, that means 1 minus z inverse in the numerator, denominator 1, this by 1. 1 minus z inverse by 1 plus z inverse, okay, or 1 minus z inverse plus 2 z inverse 2. This is rational. You can have more power in the denominator, 3 z inverse 2, 4 z inverse 3, like that. These are all rational functions. Suppose f z is something like this. Okay. As an example, so if I put this kind of form, where f z itself is a rational function of z inverse, that is, it is a ratio of two polynomials, one numerator polynomial in z inverse in power of z inverse, one denominator polynomial in terms of powers of z inverse. If you put wherever there is s, if you put this f z here, everywhere, so either this will be there or square of this, cube of this, all this will be there. When you simplify, so evidently we will get a numerator polynomial in terms of z inverse and power of z inverse, and denominator polynomial in terms of z inverse and its powers. As an example, suppose your HAS was just B0 plus B1s, and it is A0 plus A1s plus A2s square, and suppose S you are replacing by f z, which is just very simply 1 minus z inverse plus 1 by z inverse, suppose, as an example. So, if I put that back here, what will I get? H z will be B0 plus B1 into f z, that is 1 minus z inverse by 1 plus z inverse. Okay. This function I am designing, and I am saying that wherever there is s in the analog transfer function, I will replace that this function. So, I will get one digital transfer function. Okay. That is what I am getting. It is not that s equal to this, it is just mapping. Wherever there is s, I will replace it by a function of my choice. So, by this replacement of s by something, some f z, I get another transfer function. Okay. of a digital system, DSP system, and this will be like B0 plus B1 instead of S we have got this, then A0 plus A1 instead of S we have got this, then A2 square. Now, if you simplify this, you understand denominator numerator both will be multiplied by 1 plus Z inverse whole square, and so you will simplify. I am not doing it. You understand there will be numerator polynomial by denominator polynomial of Z inverse. If you want to do that silly algebra, it will be like, I mean, because here 1 plus Z inverse whole square. So, numerator denominator both will be multiplied by 1 plus Z inverse whole square. So, B0 into this, B1 into this by this, 1 plus Z inverse cancels. So, this divided by and now you break it, you get some coefficients. Okay, some if you simplify it, finally you will get maybe some. So, you will go up to what? Z inverse square. So, Z inverse 2, here also Z inverse 2, right. So, you will get something like maybe alpha 0 plus alpha 1 Z inverse plus alpha 2 Z inverse 2 divided by maybe some beta 0 plus beta 1 Z inverse plus beta 2 Z inverse 2. This is what you will get. So, one thing is there, if you are replacing S by a function of Z, and if you take that Z to be f Z to be a f Z itself to be a rational function in Z inverse, like this kind of thing or this kind of thing, then when you substitute that in place of S everywhere and then simplify, you eventually get one rational function in Z inverse. There is one numerator polynomial in powers of Z inverse divided by denominator polynomial in powers of Z inverse, because I want the digital transfer function to be rational. So, I get a rational digital transfer function in this way. So, if an analog filter is designed, and from that a digital transfer function is to be derived, we replace S by wherever there is S, we replace by some function of Z which is a rational function in Z inverse. Okay, then at least one thing is assured, we get a rational function in terms of Hz, okay, rational Hz. So, we are actually considering this, that there will be to start with one analog filter design called prototype filter, which is rational, which is causal, which is stable, and from that we want to derive in this procedure one digital transfer function by replacing S wherever S occurs by one function f of Z of our choice. But I want Hz thus derived to be rational in Z inverse. So, here by this example you see that if f Z is a rational function in Z inverse, that is a ratio of two polynomials in Z inverse, powers of Z inverse, then when you substitute S by this and simplify, you get a rational Hz of this kind of form, right. So, henceforth we will choose f Z to be rational, that is one thing is there. Next, we can also write H A S as numerator polynomial N S divided by denominator polynomial. Denominator polynomial is this you can factorize into first order factors. One factor I separate out, one factor maybe S minus say S naught, and remaining ones, because we will study only one pole at a time, S equal to S 0 is a pole, remaining all factors are put into one are combined to form one another polynomial, maybe d prime S is degree is 1 less, because one factor has gone out. Okay. So, here in this form if I write H Z, it will be n in place of S everywhere it will be f Z. So, n S is a polynomial, this polynomial in S powers of S wherever there is S replaces by f Z. So, you get whatever you got there earlier. Okay. In the case of denominator also d prime, so wherever S you replace S f Z is rational in Z inverse. So, this n of f Z will be rational, d prime f Z will be rational, and everything will be rational. But here f Z S is f Z minus S naught. Okay. So, earlier in terms of S there was a pole at S naught. So, in terms of f z, for what value of z, f z will be S naught, that will be a pole in terms of f z. That is, if you solve this equation and find out z, that will be a pole in terms of z, because for that z, if you take that z, put that in f z, that f z is equal to S naught, because that is how that z is obtained. You can call the solution to be z naught. So, f of z naught is S naught. So, h of z naught, if I want to find out, I have to have f of z naught, but that is S naught, but that is how z naught is obtained, and S naught minus S naught 0, which means you solve this equation and find the solution, and this solution will be your new pole. Now, I want my original pole, my original system was causalar stable, therefore, pole S 0, if S 0 had sigma 0 plus j omega 0, then I know sigma 0 is negative. That is, the pole should be on the left hand side of the j omega axis. So, sigma 0 should be negative. Okay. So, if it is given that sigma 0 is negative, then for this H z to be causalar stable, z 0, the new pole should be such that mod z 0 is less than 1, that is z 0 lies within unit circle. There, that means, if S 0 is such, its real part is negative, that is lies in the left half plane in the S plane, then that is H s is causal unstable, then f z equal to S 0, if I solve and I get a pole, new pole z 0 in terms of z, corresponding mod z 0 also should be less than 1. That means, the pole in terms of z should be within unit circle. So, if all the poles are within unit circle, we know the system will be causal unstable. So, the f z should be such. So, there is another condition on f z. One condition was that f z should be rational, like this or like this. Now, another condition, that if you solve f z equal to some s, and if real part of s is less than 0, then this should lead to mod z less than 1, which means, if real part of s greater than 1, the system is not stable, then here also it should be greater than 1. That is, that means, if the input in the original analog system is causalar stable. So, that pole, if instead of S naught I am making more general S, if the pole is within in the left half plane, then the corresponding pole in the z domain is within unit circle, because mod is less than 1. But at the same time, if the system is not stable, analog system, that is real part of that S is greater than 0, then it should not also lead to the same mod z less than 1. That is, my H z should be stable and causal if and only if analog system is stable and causal, not when analog system is not unstable and non causal, but still I am getting on H z which is causal. No, causal and stable. If it is causal and stable in S domain, this analog domain, it should be causal and stable in digital domain, and if it is not, but not otherwise. That is, if real part of S greater than 0, analog system is, does not satisfy causality and stability both, okay. And therefore, in that case, digital system also should not satisfy causality and stability both. So, mod z should be greater than 1. So, this is one condition. Okay. That means, all left half plane poles should map within should map to poles within unit circle, which means, if this is S plane and if it is Z plane unit circle, this unit circle, this much is 1, any pole here should map to some pole here, not outside, which means entire zone should map to inside, and entire zone outside, any pole here should map to pole outside for this part, which means right half plane should map to outside unit circle in the Z plane. This is another property of f z. So, you should choose f z carefully, so that this is also satisfied, that when you solve f z equal to s, if real part of s is less than 0, corresponding z should be such as mod is less than 1. If real part of s is greater than 0, corresponding solution z should be such as mod is greater than 1. Okay. these two conditions. But how about real part of S equal to 0? This part we have not shown. This we will now consider. Suppose real part of S is 0, that means S is just j omega. S equal to j omega, which means the analog system will give rise to the, I will have the frequency response, that is S is replaced by j omega. Okay. In that case, when you solve f z equal to S, which is equivalent to just j omega, no real part is 0, only this, then I say that mod z should be, and why I will explain. Mod z should be 1, that is z should be magnitude 1 and some angle maybe omega. Why? Because suppose you make the substitution, you get an H z finally in terms of alpha 0 plus alpha 1 z inverse and this way dot maybe alpha q z inverse q. I am taking same order q, it can be larger also, does not matter, it can be q prime divided by a 0, not a 0, beta 0, beta 1 z inverse plus dot plus beta p z inverse p. I am taking same order p and q, but depends on f z. If f z has higher order terms, the numerator degrees will go up. Okay, remember that. But suppose I have substituted s by that and simplified, I got this. Okay, I want to find out is dTft at, so I want to find out H z at z equal to say e to the power j omega. That means here I have to simply replace z by e to the power j omega, e to the power minus j omega, e to the power minus j omega q and dot. That is the dTft. But I can also use this expression, and that is b 0 plus b 1 f e to the power j omega plus b 2 f square e to the power j omega plus b q f to the power q e to the power j omega. But what is f e to the power j omega? Here I am saying that if f z is such that when you solve f z equal to j capital omega, just pure imaginary part, you would get z equal to e to the power j omega, that is magnitude is 1. That means f e to the power j omega will be just j capital omega, is not it? So, that means if you want to find out dTft, the transfer function at e to the power j omega, that is alpha 0 plus alpha 1 e to the power minus j omega plus dot plus alpha q e to the power minus j omega q by dot. This you can also write equivalently as b 0 plus b 1 f of e to the power j omega plus b 2 f square of e to the power j omega dot. But f of e to the power j omega is j capital omega. That means b 0 plus b 1 j capital omega plus b 2 j capital omega square dot, which is analog transfer function at j omega, at omega. That means digital, if you solve this, you get small omega in terms of capital omega, or you get capital omega in terms of small omega. Okay. That means if you want to find out the transfer function, the frequency response at digital frequency omega, that is you replace z by e to the power j omega. What will be the value of this? You can easily find out by what? Solve for this e to the power j omega, f of e to the power j omega, find out it will be j capital omega only because of this assumption, and so this transfer function then turns out to be nothing but h a s, where s replaced by j capital omega, because f of e to the power j omega is j capital omega. So, it will be b 0 plus b 1 j capital omega, that is b 1 j capital omega plus b 2 j capital omega whole square, that is b 2 j capital omega whole square dot, as though it is h a s, where s is replaced by j omega. That means, I can find out the digital frequency response at a particular frequency small omega. How? I just put in this equation, put f e to the power j omega, I get a purely complex, the purely imaginary number j capital omega, and then the digital frequency response will be analog frequency response at that capital omega. So, I can map one response to other. So, digital response, digital filter response at a digital frequency small omega will be same as analog frequency response at S equal to j capital omega, analog frequency capital omega, where capital omega, small omega related by this, where f is your function of your choice. These are the three main important properties. So, by the last property I can transform one figure, one frequency response figure into another. That is, I have to find out, suppose this H A j omega plot is given to me. I have to find out digital filter frequency response plot. So, I start at any small omega. I have to find out what is the digital, what is H capital e to the power j omega. Okay. So, the small omega, I want to find out the frequency response at a digital frequency small omega. What do I have to do? Simply, I put in this equation f e to the power j omega, find the left hand side out. This will be equal to, by this assumption, it will be equal to just a pure imaginary number j into some angle capital omega, j into some frequency. And by this theory, then this digital filter frequency response at small omega will be same as analog filter frequency response at that capital omega. There is b 0 plus b 1 j capital omega plus b 2 within bracket j capital omega whole square and dot 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 dot. Okay. That is because the moment you put small omega here, okay, instead of taking this form, H j I can write in this form also, they are equivalent, but here b 1 f e to the power j omega, f e to the power j omega means j capital omega, b 2 j capital omega whole square and dot dot dot, as though b 0 plus b 1 into j capital omega plus b 2 into j capital omega whole square dot dot dot. That is this analog frequency response at j capital omega. So, therefore, small f should be such that when real part of s is 0 and s is just j capital omega, then the solution of this equation m z equal to s should give rise to a solution whose magnitude is 1 and z should be e to the power j omega, which means f of e to the power j omega should be a pure imaginary number. Okay. Or if you are solving f as f z equal to a pure imaginary number, corresponding z should be having mod z 1, it will be just e to the power j an angle. So, these three properties, by this we can transform any analog filter into a digital filter. Okay. One example is a famous example called bilinear transformation. I do not think I have time to cover it, but I can just give you a formula. S to be replaced by f z in an analog rational function, rational transfer function, which is rational, causal unstable. In this, I know they have to replace S by some f z, which should be rational in Z inverse. Okay, and it should satisfy the other two property. That is, if S real part is negative, then the corresponding solution, okay, f z equal to S, it should give rise to a solution Z whose mod is less than 1. So, that pole on the left half plane maps to a pole within unit circle in the digital plane, in the digital, and so and so. And one more property which we discussed. This f z in this example is bilinear is 2 by t, t is your choice, you can view it as a sampling period 2 by t, you can take it to be 1 also, 1 minus z inverse plus 1 by z inverse. Take this form, firstly it satisfies condition 1, that is rational, because it is a numerator polynomial in z inverse, denominator polynomial in z inverse. So, first condition is satisfied. Then 2 by t 1 minus z inverse by 1 plus z inverse equal to S, S as sigma plus j capital omega. Okay. We will see if sigma is negative, corresponding z should be such from this equation, that is there is a pole which is on the left half plane in the S plane, that is sigma is negative. Then if you solve this equation, it will give rise to a pole in the z plane whose mod is less than 1, that is it will be within unit circle. We will see this. How to obtain this? So, 1 minus z inverse by 1 plus z inverse is S, I am writing in the form of S now, S t by 2. So, if you add 1 to it, you get 1 plus z inverse plus 1 minus z inverse. So, 2 by 1 plus z inverse is 1 plus S t by 2 by, if you add 1 to the left hand side and 1 to the right hand side, what happens? 1 plus Z inverse plus 1 minus Z inverse. So, Z inverse cancels, 2 by 1 plus Z inverse, that is 1 plus S t by 2. And if you subtract it from 1 minus this, then what happens? 1 plus Z inverse minus 1 plus Z inverse. So, it will be 2 Z inverse by 1 plus Z inverse, and subtracting right hand side from 1 means 1 minus S t by 2. Okay. If you divide this by this, then obviously divide this by this, which means that this will cancel, and 2 by 2 Z inverse means Z. 2 cancels, 1 by Z inverse, that is Z, that will be 1 plus S t by 2 by 1 minus S t by 2, and now 1 plus sigma t by 2 plus j omega t by 2 divided by 1 minus okay. So, what is mod z? Mod z will be mod z, mod z says take square, otherwise you have to take a square root. A plus j b, its mod is square root of a square plus b square. I do not know the square root, so take a square. So, mod z will be what? Mod of numerator divided by mod of denominator. We have already seen last time. So, I am taking extra mod square, so square root will not be required, or if you want you can put a square root, does not matter. This is real part, so a square, and this is by a, so b square. Now, suppose sigma is negative. If sigma is negative, it will be 1 minus some quantity, and it is 1 plus the same quantity. This is same as this. So, it does not, it is common, but if it is 1 minus a quantity and 1 plus the same quantity, then this will be less than this, which means then, so if sigma is less than 0, obviously mod z is less than 1, because numerator is less, denominator is more higher, because it is actually minus, like say sigma is minus 2. So, it will be 1 minus, say sigma is minus 1, 1 minus t by 2, it is 1 plus t by 2. This part is common in both numerator and denominator, it does not change anything. So, numerator becomes less than denominator, that is mod z less than 1. On the other hand, if sigma greater than 0, mod z greater than 1. So, this satisfies the condition number 2, that is any s on the left half plane, that means any s for which sigma less than 0, corresponding z will be such its mod z is less than 1, that is it will be within unit circle. And if it is on the right half plane, in the s plane, then the corresponding z will be outside the unit circle, which means entire left half plane, that is the entire s plane to the left of j omega axis will be mapped within unit circle in the z plane, and entire area to the right of the j omega axis in the s plane will map to the outside of the unit circle in the z plane. The third condition, when s is just equal to j omega, what happens to z? Does it have magnitude equal to 1, and therefore z equal to e to the power j omega? This we will verify in the next class. Thank you very much.